Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to walk through an example of how to analyze impacts. So let me talk a little bit about what we're looking for. You need to focus on the picture on the left, this stuff. So this is kind of a snapshot in time, and at the instant shown, this car, which I'm calling car A, is moving at 10 meters per second. It's 1,500 kilograms. It's creeping up onto this Subaru looking thing here, which is what I'm calling car B, moving at 7 meters per second, and car B is 1,800 kilograms. So what we're going to do here is we're going to imagine that car A hits car B. After the impact, car A is now moving at 8 meters per second. We're going to try to calculate a couple things. First, we're going to try to calculate the velocity of car B after the impact. And second, we're going to calculate the change in kinetic energy of the system. All right, now, in theory, when you're analyzing a problem, the first thing you do is you start with a picture of what the system looks like before impact. And because it's an impact problem, momentum is going to be a very important concept. Remember, momentum is mass times velocity. So because velocity is important, I'm going to go ahead and draw velocity vectors here. Car A is moving to the right, so it's got a velocity vector that I would call VA1, and I can probably write that a little better than that. VA1. In this example, that'd be 10 meters per second. Car B also moving to the right, so I'm going to give it a velocity vector. Call that VB1. In this example, VB1 would be 7 meters per second. So when you're analyzing an impact, first thing you do is draw a picture of the system before the impact, put velocity vectors in. All right. Then you draw a picture of what the system looks like after the impact. So after the impact, car A here has a new velocity vector. I'm going to call that VA2 for velocity of car A picture 2. And car B here has a new velocity vector. I'm going to call that VB2, velocity car B picture 2. Now I'm taking a guess here, because of the impact, the force direction on car A is going to be to the left. Therefore, I believe that VA2 will be less than VA1, and I tried to show that with a shorter vector. The force acting on car B is going to be to the right, so I'm expecting that velocity to increase, and I tried to demonstrate that with a larger velocity vector here for VB2. Right? Key concept here is that when these things impact, the force on car A is to the left. So if I drew a force vector during the impact, it would be to the left, and the force on car B would be to the right. Very, very important thing to realize is as long as we define our system as both cars together, the net force during impact is 0, which would allow us to say that the momentum of the system is conserved. So what we're going to do is we're going to write an equation, conservation of momentum. Momentum, remember, is a vector quantity, so we have to dictate plus and minus signs by direction. I'm going to go ahead and call right positive for this equation. And what I'm going to do now is equate the momentum in picture 1 to the momentum in picture 2. So car A's momentum, if I write it out algebraically, is MAVA1, and it's positive because car A's momentum points to the right, and I've got right positive. Car B's momentum can be written MBVB1, and it's also positive because it also points to the right. Right? All right, after impact here, car A's momentum is MAVA2. It also is positive because it points right. Car B's momentum is MBVB2. It also positive because it points right. And again, the reason we can put the equality here, very important to understand. Why can we do that? Because of how we're defining our system. It goes back to the system. As long as we consider our system, both cars together, that the force of impact on car A is to the left, on car B is to the right. But as long as we consider both of them at the same time, the net force on that system is 0. That's an internal force. That allows us to put the equality here between these momentums. Now, numerically, I'm going to go ahead and write this out. This is going to be, go back and write it in black here. This is going to be 1,500 kilograms times 10 meters per second plus 1,800 kilograms times 7 meters per second equals, let's see, car A here, that's going to be 1,500 kilograms times VA2, which in this example is 8 meter per second, plus mass B, 1,800 kilograms, times VB2, which is an unknown quantity here. And I'm going to go ahead and take a moment and solve that for VB2. Give me a moment here to work with the calculator. Okay, plus. Okay, I got 8.67 out of that for VB2. So that should be the speed of car 2 after the impact. All right, now we're going to work on the loss or the change in kinetic energy of the system. Now, momentum is mass times velocity, and kinetic energy is 1/2 mv squared. So each of these momentum terms will have a kinetic energy term. So what I'm going to do is right under each momentum term, calculate a kinetic energy that goes with it. So I got 75,000. I'm going to just write 75 kilojoules for that, all right? And I got that by taking 1/2 m times v squared. So 1/2 times 1,500 times 10 squared is where that came from. I'm going to write it in units of kilojoules just to make it a little shorter to write, all right? Then the next term is going to be 1/2 times 1,800 times 7 squared. Okay, and I got 44.1 kilojoules. All right, and that came from 1/2 1,800 times 7 squared, and again I wrote it in units of kilojoules. So adding those together, right, so I get 119.1 kilojoules. I'm just going to call that 119 kilojoules. That's the total kinetic energy of the system before impact. I'm going to come over here and do the same thing now. 1/2 times 1,500 times 8 squared. Okay, I get 48 kilojoules for this momentum term. And then for this guy, let's see, 1/2 times 1,800 times VB2, which remember was 8.67, squared. And I get 67,652. I'm going to go ahead and write that as 67.7 kilojoules. And again, these add to 115.7. I'm just going to round that to 116. So this is about 116 kilojoules. Now you notice the system started with 119 kilojoules. It ended with 116 kilojoules. All right, so the loss here is 3 kilojoules. So the change in kinetic energy, oops, write that a little bit better, all right, is equal to KE final, 116 kilojoules, minus KE initial, 119 kilojoules, which is negative 3 kilojoules. Expressed as a percent, the percent loss, whoops, we would get by taking the loss, 3 kilojoules, I don't need the minus sign, I know it's a loss, divided by what we started with, 119 kilojoules. Right, as a decimal, that value is 0.025, 0.0252, or as a percentage, that would be 2.5%, or 2.52% of the kinetic energy was lost. Typically in impacts, a higher percentage of the kinetic energy was lost. The reason here we had such a low percentage of kinetic energy, this was a relatively low speed impact. I made the example up in such a way because I didn't want anybody in these cars to get hurt. The higher the impact speed, typically the more material is deformed, and therefore you would have a much higher loss in kinetic energy. So this is an example of an impact that was almost an energy conserved impact. And again, when you're talking about automobiles, anytime you have permanent deforming of material, typically kinetic energy, significant amounts of kinetic energy are lost. So you always want to start with momentum. So let me go over this again. Analyzing impacts. The first thing you do is draw a picture of the system, like a snapshot in time. Draw velocity vectors for each part of the system just before the impact. Next thing you do, draw a picture of what the system looks like after the impact, including velocity vectors, and you have to label them in some way, shape, or form. Next thing, typically you would write a momentum conservation, and you need to define the system in such a way that the net force is zero. So if it's an impact, you're going to want this equation to include all parts. Right? In this case, it's a pair of cars, but it may be other objects. And then when you write the momentum equation, you got to take into account plus and minus signs. In this example, I was doing right positive. Every velocity vector is to the right. That's why I've got no minus signs here. But we may have another example where maybe this car started before the impact moving left. That would make this velocity negative. It would make that momentum term negative. So just keep that in mind, that you dictate the plus and minus signs like you would any other vector. Right? Typically you can solve for a velocity or maybe some other type of unknown, and that's how you apply momentum concepts. As far as questions regarding losses in kinetic energy, each momentum term will have a kinetic energy that goes with it, because momentum is mass times velocity, and kinetic energy is 1/2 mass times velocity squared. So what I typically do is wherever I have a momentum, I calculate a kinetic energy. Here's another momentum term, calculate a kinetic energy. The sum of these two is the total kinetic energy before the impact. Same thing over here. This momentum, we can calculate a kinetic energy for this. We can calculate a kinetic energy for this. The sum of the two is the total kinetic energy after the impact. You'll notice I did not put an equal sign between these. That's because I did not expect them to be equal. Typically, the kinetic energy before an impact is greater than or equal to the kinetic energy after the impact, because there's almost always going to be a loss in kinetic energy before and after an impact. Sometimes there's equality. Again, in your homework you're looking for the word elastic. If you saw elastic, there would be a equality there. I'm going to change this A and B to initial and final so as not to be confused with car A and B. So typically your kinetic energy, your initial kinetic energy will be greater than or equal to your final kinetic energy. And again, because there's usually loss. As far as the actual equality, in your homework you're looking for the word elastic. In reality, you're looking for impacts where the material is very, very hard and there's no permanent deforming of material. Anyway, hope that this video helps. Have a great day.